Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 68. Now, in this lecture, we are actually going to be beginning a new topic. Okay. Now, so far, until lecture 67, for a long time now, for approximately a good 40-ish lectures, okay, right? Until lecture 67, for the past 40-ish lectures approximately, we were concerned with detecting molecules in space, right? And we saw that this involves so many branches. You had astronomy, right? You had spectroscopy, and as part of it, you had to understand quantum mechanics, you had to understand a lot of statistical thermodynamics, and as part of astronomy, you needed a lot of classical physics, some optics and thermodynamics. Optics, and also, although we did not look into the optics aspect, we shall be looking into some aspects of it in the tutorials. Okay, a lot of classical physics, optics, and these are all interconnected. All these areas can be interconnected, right? So the idea, if you go to the very first lecture, I was telling you that astrochemistry is a highly interdisciplinary science, and so understanding astrochemistry requires understanding in great depth all these subjects also, correct? Okay, a lot of these interrelated subjects. So that's kind of what we did, until now, where I gave you a glimpse of all of these aspects, right? A very faint glimpse rather of astronomy, right? Some aspect of spectroscopy, the necessary quantum mechanics for it, the necessary statistical thermodynamics in the form of Boltzmann distribution, the local thermal equilibrium, etc. Some optics, right? Some optics, very small amount of optics, but we will take care of some optics aspect in the tutorials, okay, right? In the tutorial. So I just want to teach you just one or two pending broad, big picture aspects concerning things such as the line of sight, or the column density, and then to get the number density in terms of per centimeter cube, and also, what is the spectral and spatial resolution, and lastly also about some components of radio astronomy. We've never looked into the instrumentation part of it. So those things I will look into in one or two tutorials. Okay. So for now, we have kind of completed this module of detecting molecules in space. Okay, right? So next, what we are going to be looking into is the chemistry and chemical reactions in space. Chemistry and chemical reactions in space. Okay. Again, I highlight that this was what we could do justice, right? In 40 lectures we did, because each of these individual topics, could be a separate master's level or PhD level course. But to do that, you needed the background of this course. Okay. So that's why I highlighted all those aspects. Okay. Let me state it very precisely that at the undergraduate level, enough background was provided, right, in each of these topics, noting that each of these topics, okay, right, astronomy, spectroscopy, classical physics, optics, quantum mechanics, statistical thermodynamics, etc., right, each of them is an individual research area in astrochemistry. Okay. So what I've written here is each of these areas is a different individual research area itself. Please note this point. Okay, right? So that is why we couldn't go in depth in any of these aspects. All right. Although a few more aspects of astronomy will be discussed in 1 or 2 tutorials max. Okay. So now we move on to chemistry and chemical reactions in space. Now go back in time to probably you can just take a look at that video. Probably around lecture somewhere in the late teens or early 20s or something like that. I told you that the simplest reaction, right, that one could imagine, that is, for example, let's say the formation of H2, right? H2 in the gas phase from H gas and H gas, which actually liberates a lot of energy. The delta E for this process, if I recall, is close to negative 430 kilocalories per mole. Okay, right? You just go back and verify this number precisely. Okay, right? Now, it does not happen in the ISM. You may be astonished. Why does it not happen? Well, I was telling you, right? I was telling you that the reason why this does not happen is, even though, this liberates energy, that is in the chemist sign convention, liberation of energy is given a negative sign, okay, right? Even though this process liberates energy, the problem is that the interstellar medium is a very sparse environment, okay? So, due to that reason, whatever excess energy is obtained with this molecule, it has to dissipate it back to the system, sorry, okay, right? This excess energy, once H and H form H2, right, has to be dissipated back to the surroundings. Once that is done, right, there is no other molecule to take this energy, or there is no radiative mechanism to just simply radiate the excess energy. In the absence of this, right, even though this is an energetically favorable process, it does not happen because as soon as H2 is formed, it goes back to give you H and H, right? Are we clear? In other words, I'll explain it here. Because the ISM is sparse. What do I mean by sparse? Well, the number density is very low there, okay? So because the ISM is sparse, even though energy is released, okay, right? Energy is released in the formation of H2 gas in the reaction H gas H2 gas, right? Even though in this reaction energy is released, there is no way to dissipate the excess energy that is with H2. Energy with H2 gas once it is formed, okay? With H2 gas, once it is formed. Therefore, what happens is that it just dissipates all of its energy to the surroundings, and consequently, this implies that even if H2 gas is formed, right, it immediately dissociates back to give you the reactants, okay? So, which implies that H2 gas, even if formed, gives back H gas. This is a very important point, and that is why, if you even recall the earlier stages of this course, even when we were discussing about Big Bang nucleosynthesis, etc., it had to be reaction of the form A plus B giving C plus D, right? It cannot be of the form A plus B giving C alone, right, in the gas phase, because you have to find a mechanism to dissipate the energy. Okay. Now, H2 could either radiate the excess energy. Well, for H2 gas itself, there is no mechanism via which it could radiate, and or it could pass it off to another molecule. But because this sparseness of the interstellar medium, there is no fellow product to which, like H2 gas could give its energy off. So therefore, what happens is that whatever energy is gained in the process is completely given back to the surroundings, which results in the dissociation of H2 once again to form the two gaseous space molecules. The gaseous state molecules, sorry, not space. Okay, right? And so therefore, even the simple reaction does not occur in the ISM as we have written it here. Okay, how else does it occur? So this is where interstellar surface chemistry becomes very important. I'll explain it to you. So this is where interstellar surface chemistry becomes very important. Let's see, how it works out. But before that, I want to describe to you briefly what the surface is in the context of an interstellar medium. Now, if you go back to recall, if you actually go back to the first few lectures, I was telling you about the composition of the ISM, right? The ISM is predominantly what? Hydrogen and helium in the gas phase. But roughly 1% of it is in the form of solid dust, approximately 1% of ISM is dust. Well, what do I mean by dust in this context? By dust, I'm talking about some solid. It could either be amorphous or crystalline, okay, right? It is some solid which has a surface on which chemical reactions can happen, okay? So what we shall do next is, I will briefly tell you the composition of this solid surface, okay, right? And then I'll explain to you how it facilitates this otherwise implausible reaction in the ISM, okay? So broadly speaking, okay, some kind of a rough composition of interstellar dust, okay, right? We're talking about some kind of a surface, solid surface. So at the core, let's say this is some core, okay? I mean, this is just a pictorial depiction of some core. At the core, you have, refractory inorganics. For example, you have stuff such as silicon oxides, titanium oxides, etc. Okay, right? Something like this, okay, right? So you have, remember, I told you the importance of silicon oxides approximately somewhere around lecture 20 in some tutorial, I forgot, okay, right? You may just go back to the videos and look back. So how are these silicon oxides formed? See, whenever a molecular cloud is formed, a molecular cloud is formed from a protostar, right? A molecular cloud can also be formed from a dying star, okay? A protostar is something that talks about the beginning stages of a star. Similarly, a dying star also, right? All the material from the they just accrete together, right? While a star collapses, or when a star is getting formed, right? When the silicon rich part accrues into one particular region, it also gets along some oxygen. Why is it? Because the silicon oxygen bond is very strong, and silicon has this tendency to catenate, right? It forms polymeric networks. We saw that, right? So whatever silicon oxide that is formed from the star, right? They just agglomerate together to form this core of the interstellar dust. Of course, it is also to be noted that predominantly a lot of silicon oxide, titanium oxide, etc., they all go and become parts of meteorites. But there is some leftover silicon oxide and titanium oxide and other refractory inorganic substance which forms the core of this interstellar dust also. Okay, please note this point. So therefore, the core is going to be composed of the silicon oxide and titanium oxide, etc. And you have some icy mantle. Okay, I'll just so this is the icy mantle. Okay, right? Icy mantle. When I say icy mantle, you have attached to the silicon surface some kind of organic substances, such as, for example, you can think of carbon monoxide, methanol, formaldehyde. So, see, these are not going to form such strong polymeric networks such as silicon oxide. But what they do is they form via weak interactions. They form ices. Recall, even in our discussion of asteroids versus meteorites, right? We were talking about the ices being much weakly bound. These are much more volatile in relation to this refractory substances. Okay, so some of these icy substances, they form the mantle around this core silicon oxide agglomeration. Okay, right? So we have an icy mantle around the dense core, and atop this, very light atoms and molecules can adsorb. So you have the icy mantle, and let's say we use the dashed lines to represent the icy mantle. Okay, right? And let's use the dots, just some dots. Okay, right? To represent the adsorption. Adsorb single molecule, small molecular atoms from the gas phase, right? So a lot of the ISM is going to be gas phase, right? So molecules from all atoms from the gas phase can get adsorbed on to the ices, right? Now, the ices are more prominent in the dense molecular clouds, but in the diffuse molecular clouds, you don't have this prominent icy mantle. It is majorly composed of the silicon oxide or titanium oxide core itself. So the point is, a lot of small molecules and atoms, such as, like, for example, prominently, example, H atom, right? So that can adsorb. So the dots represent the small molecules, for example, the H, etc., which get adsorbed. What is the meaning of adsorption? Well, a working understanding is adsorption is nothing but single layer absorption, right? If we're talking about a three-dimensional structure here, right? In other words, there are many layers. But when the H atom just sticks onto the first layer, the top layer, that is of the icy layer here, right? We call it as adsorption. Okay, so the small molecules can adsorb onto these ices, which are part of the surface. Okay, right? Sometimes the ices can independently, exist also in very rare cases, but let's not worry about that. So this is the overall structure of interstellar dust, especially in a dense molecular cloud. In a dense molecular cloud. Okay, so please note this point. The key idea is that the surface, therefore, provides sites for individual atoms and molecules, right, to get adsorbed. We will see its consequence in chemical reactivity very soon. Okay, so this is the broad idea of the composition of the interstellar dust surface, and the dimension, is roughly of the order of let's say around 10 to the power minus 6 to 10 to the power minus 7 meters, approximately 10 to the power minus 7 meters, let's say. Okay, right? So these are the dimensions. Well, the exact shape, the exact morphology is all a question of speculation, but nonetheless, based on spectroscopic experiments, that is astronomical experiments, we have a broad idea. We have a broad idea that this is the broad composition of an interstellar dust surface. Okay, now let us see how this dust surface leads to chemical reactivity in space. We'll use the example of the formation of H2 molecule. What we're now going to look into is the formation of hydrogen onto the surface. Let's say that there were lots of hydrogen atoms in space in the ISM. It's a fair statement, correct? Now, let's say some of the hydrogen atoms get adsorbed onto the surface. Okay, let me just call this one layer of a surface. I'll just draw this to be the surface, okay, right? I mean, some circle to be the surface. And let's say that one H atom from the gas phase, correct? H atom from the gas phase gets absorbed onto the surface. Let me just call this HA. So the HA from the gas phase gets absorbed onto the surface. I mean, this surface has different layers. It's of varied thickness, etc., etc. Now let's say that one more hydrogen atom, in a different direction gets absorbed. This is the surface, right? This is the surface. And let's say some HB, again from the gas phase, gets absorbed onto the surface in a different orientation. See, the surface is three-dimensional, right? So the hydrogen atom can get absorbed from any direction. So now what happens is, inside the surface, let's say this is step 1. So what is happening? 2, just for the sake of nomenclature, I have labeled them as HA and HB, okay, right? HA gas and HB gas, right, get adsorbed. Right, so this is step 1. Now what happens is, in step 2, let's say that HB, diffuses, right? See, one amazing thing about these surfaces is that it provides a path for the H atoms to diffuse, okay, right? So the surface provides, let's say, a platform, that's the right word, okay, a platform or a paradigm, or a scaffold, okay. Scaffold for smaller atoms or molecules to diffuse to the surface, okay. So via diffusion, which I'm just going to say something like this, okay, just to indicate diffusion. You get me, right? This wiggly line to indicate diffusion, and let's say that my HA and HB, let's just call this HA and HB, are brought together, okay, right? They are brought together, and once they are close enough together, right, then what happens is that in step 3, I'll put it this way. This is step 2. Now, then what happens is that both these H atoms, they just combine together, right? So, and then they leave the surface by desorption. The exact details, it depends on the dust composition, the temperature, pressure, etc., etc. But broadly speaking, what can happen is, let's say, you have HBHA. They are close enough that they form a bond and are weakly adsorbed still, okay, right? Then H2, just desorbs, because there are going to be mechanisms by which the dust gets cooled and heated in the interstellar medium, right? For example, the presence of various interstellar radiations, or simply by bombardment by cosmic rays, etc., etc. So then what happens is, this is step 3, and in step 4 you have desorption. This is just the surface plus HAHB in the gas phase. Are we clear? Okay, so this is step 4, which is desorption. So what are the 4 steps broadly involved? Well, first, molecules or small atoms, they get adsorbed onto the surface, point number 1. And followed by this adsorption, what happens is diffusion happens, right? And via diffusion, HA and HB come close enough. And once they come close enough, there is a thermodynamic impetus to form a bond. The exact energetics I will explain to you in let's say, in about 1 or 2 lectures, and followed by desorption, you get the formation of H2 molecule. Now, what have we accomplished to this? What have we accomplished to this, which was a challenge in the direct synthesis? Well, I'll state it here. I'll call this page number 7. Through the participation, okay, right? Through the participation of a surface, I'm just calling it S, okay, right? Now, we have provided a third body to dissipate the excess energy that is associated in the formation of H2, right? In the excess energy in the formation of H2 gas. In other words, what is that I'm telling? What I'm telling is that H gas plus H gas, okay, right? Plus some surface, right? Where I'm just calling this some surface S. So that's why it's an effective third body. Even though, see, 3 particles cannot collide in the ISM because how do chemical reactions happen? Chemical reactions happen by atoms and molecules colliding with one another, okay? But the collision of 2 particles itself is going to be very hard in the ISM. So, but by introducing one more entity, it's just going to be exceptionally hard, okay? So directly 3 body collisions are not going to happen. However, the surface acts as a third body, okay, right? The surface acts as a third body effectively to give rise to H2 gas plus S, such that the excess energy is dissipated to the surface, right? Whatever excess energy is available here, right, in the formation of H2 is just absorbed by the much larger surface. So that is why this provides an alternative pathway. It provides an alternate path, an alternate feasible path for the formation of H2 gas overall. So now do you see the importance of interstellar surface chemistry? Okay, right? This was just one example. Now, in the next lecture, we should also be briefly talking about the formation of some organic species on interstellar surfaces. And I'll also briefly talk to you about some gas phase chemistry happening in the ISM also, and how the gas and solid phase chemistry in the ISM are intricately connected. Okay, so on that note, I'll summarize what we saw in this lecture. I introduced you to a new topic, that is the chemical reactions happening in the interstellar medium, and I told you that the interstellar surface chemistry is a very important aspect via which even the most fundamental molecule, that is H2 gas, how that is getting formed. What are the key steps herein? It is that, well, first, the surface provides sites for adsorption, and by diffusion, the atoms are brought together, and by desorption, right, the molecule formed just escapes. And what is the big picture gain that we have obtained by involving a surface? It is that the surface acts as an effective third body, which is otherwise impossible under interstellar conditions, right? And it also takes away the excess energy that is associated with the formation of H2 gas. All right. So this was a summary for this class, and we shall discuss more in the upcoming lectures. Thanks a lot.